internal constraints can represent the connections between objects. So examples would be, say, welds and rigid connections, or possibly pin connections. And today I'd like to do a video lecture that really addresses this. I'm Dane Quinn from the University of Akron, and this is my series of video lectures for engineering mechanics. Today I'd like to look at the following two systems, and these are obviously very similar. In each case, I have a bar of mass m1 and length L that's pinned at the origin, and a disk of mass m2 and radius r that is connected at the end of the bar. Now, the difference here is that in this upper figure, this connection is rigid. Effectively, the bar and the mass, or the disk, are welded together. While in the lower example, I have a pin connection. So the disk is free to rotate at the end of the bar. But of course, it moves along as the bar moves as well. So each of these is supported on the other side by a spring of stiffness K and a damping coefficient B. And here I want to find the linearized equations of motion for each system, right? So we're just looking at small displacements of the bar/disk combination. Here, I would like to consider the bar and the disk as separate objects. So we'll consider them separately. We'll denote the bar by B and the disk with D. Seems to make sense. Now, I did a video lecture previously where I looked at a very similar object, basically a disk at the end of the bar, and they were welded together. And I talked about how you could consider this as one single object by looking at the moment of inertia of the combined pair, right, about some point. Again, I want to do this problem differently in this case. I could do that again here, right? But I really want to treat the bar and the disk separately so I can look at the internal connections, the reaction forces, and the reaction moment that is produced in this case. So, of course, the bar is pinned at O, right, the origin here, and it rotates about this point. So I only need a single coordinate to describe the configuration of the bar. And the one that we'll ultimately use is the rotation of the bar. If I have a rigid connection, then if I know the orientation of the bar, right, so if I know the angle here of the bar, then I also know everything about the disk, right? So if we have a rigid connection, we have a 1 degree of freedom system, right? I only need this one coordinate to describe everything, right, the bar and the disk. But if I have a pinned connection, actually I have 2 degrees of freedom here. One coordinate could be used to describe the angle of the bar. That's fine. Of course, that would specify where the center of the disk is, but because the disk is still free to rotate, I would need a second coordinate to describe its configuration. So again, with a pinned connection, I actually have a 2 degree of freedom system here because the disk can rotate independently from the bar. Now, we'll assume, as given here in the problem statement, that static equilibrium is horizontal. Right, so we have this horizontal static equilibrium position, which means that I am going to neglect gravity. So we won't be adding in any kind of gravitational load, and we also will not consider the static deflection of the spring. So in this case, the gravitational moment cancels out the static displacement in the spring. In particular, it cancels out the moment due to the static displacement of the spring. And again, when I talked about that composite object in the previous lecture, right, I also went through and gave some detailed explanations of how this works, right? So you can go back and refer to that. Okay, so let's start in on the process. Well, the first thing we want to do is identify our forces that act on the system, right? So here I have the two objects that we'll consider separately. And again, I want to break these up and show how the pin connection differs from the rigid connection, right? So as best I can, I'm actually going to treat these two problems. Again, let's go back and look at them. I'm going to treat these two problems kind of together. And only later in the discussion will we separate this problem from this problem based on what's happening here at the pin connection, right? So note that each force or each system has a spring and a damping force, right, at one end. So we'll just add those together, acting here at point A. Then we have O, the origin, and we have a reaction force acting at the origin. I'll note the mass center of the bar, G, and then finally we have the end of the bar at B. And of course, the end of the bar and the center of the disk are connected, right? So on the disk, right, point B is also here at the center. At point B, on the bar, we have an internal reaction force. We'll call it P. Because that's internal, we have a force of equal magnitude but opposite direction, right? So that'll be minus P acting on the disk. Likewise, we have a reaction moment acting on the bar, and then we have a moment with equal magnitude and opposite direction acting on the disk. Again, P and M are internal, right? So if I cut the disk away, I replace the disk by this reaction force and moment, and then acting on the disk, I basically have the negative of that reaction force and moment. So again, in this problem, we have forces from the spring and damper, and those act at A. We have a reaction force at point O, right? That's the pin between the bar and the ground. And then we have reaction at the end of the bar between the disk and the bar, right? So that's going to be P and M, right? The reaction at O we'll call R. And then for the spring and damping force, that's Fs and Fd. Now let's look at what happens depending on the connection between these. If it's rigid, then we have a reaction moment, right, which we've referred to as M, that serves to constrain the rotation of the disk and the rotation of the bar. So in particular, the rotation of the bar and the disk are identical. Because they're welded together. The other case that we want to look at is a pinned connection. In this case, there is no reaction moment. Which means that M is equal to 0. Because, of course, pins can't support moments, right? This disk is free to rotate. So here we see the difference between these two internal constraints. For a rigid constraint, right, we have a moment. For a pin connection, we have no moment. Now we look at coordinates and directions. Okay, directions, like always, will define I and j as fixed in the ground. And then because this bar rotates, we'll define a direction E1 and E2 fixed in the bar. Right? So again, I and j are fixed in the ground, while E1 and E2 are fixed directions in the bar. Now let's look at coordinates. We're considering the bar and the disk as separate objects, so we need coordinates to describe the motion of each. Okay, well, for the bar, let's use the angle theta to describe the inclination of this bar with respect to the static equilibrium position, which, of course, in this problem is horizontal. Then, let's look at the kinematics of the disk. Well, we're going to need to know where the mass center is. So let's measure the displacement of the mass center in the vertical direction as y. And then we'll also need the rotation of the disk. Let's call that phi. I'm trying to do these two problems together, so we need to consider and we need to allow the disk to rotate independently from the bar. Now, having said that, this also brings up our difference between the rigid and pin connections. If the system is rigidly connected, then the rotation is the same, right? So phi, the rotation of the disk, is equal to the rotation of the bar, right? And this is our constraint equation when we have a rigid connection. Just like when we had a pin connection, we saw that the constraint equation reduces to m is equal to 0. If there is a pinned connection, well, then we can't say anything about the relative rotation of phi and theta, right? So the bar beta and the disk d rotate independently. And again, there is no connection and no relationship between these two angles. Okay, so finally, we need to look at the forces. All of these reaction forces and internal forces are unknown, right? So they do not require a coordinate, but the spring and the damper do, right? They depend on the stretch across those elements as measured again from static equilibrium. So we'll call that Z. Again, here Z is the stretch of the spring, and we can also use that to determine the force in the damper. Okay, so now I've got all the coordinates, got directions. Let's go to the kinematics. So here I have rewritten the definition of the coordinates, and we have a number of constraints, right? Because we can relate the motion of the center of the disk, right? So that's y, and the motion of, or the stretch across the spring, which is z, to the rotation of the bar. And of course, we're going to do that using the velocities like we often do. So let's start off and look at point A. Right, so here, the velocity of A is the angular velocity of the bar across the position of A with respect to O. Here, the angular velocity of the bar is just theta dot in the k direction, and the position of A with respect to O is minus L over 4 in the E1 direction. So when I work through this cross product, k cross E1 is E2, right? So we end up with minus L theta dot over 4 in the E2 direction. Then the velocity of B is the angular velocity of the bar, again, cross the position of B with respect to O. So just like before, we get theta dot as the angular velocity, and then 3L over 4 in the E1 direction, well, that's the position of B with respect to O. Again, the problem statement said that this distance was a quarter of the way down. Right, so what's left? Well, 3/4 of the way. And this becomes 3L theta dot over 4 in the E2 direction. We can now relate the velocity of A and the velocity of B to z dot and y dot respectively. So assuming small displacements, right, so assuming the angle of rotation for the bar relative to static equilibrium is small, well, that implies that we are linearizing. So when we linearize the motion of A and B, we find that the velocity of A is minus z dot in the j direction, and the velocity of B is y dot in the j direction. In addition, right, for this sort of small angle displacements, E2 is approximately j. So I can set the velocity of A equal to the velocity of A. Well, I can always do that, but now we find that minus z dot in the j direction is equal to minus L theta dot over 4 in the j direction. Again, E2 is approximately j. So z dot is L theta dot over 4 when linearized. Likewise, we can do the same for y using these two expressions, and we find that y dot is 3L theta dot over 4. So these provide our coordinate relationships, our coordinate constraints between z and y and theta. Now, for the kinematics of the bar, we can identify the angular acceleration as theta double dot in the k direction, while for the disk, the angular acceleration of the disk is in terms of phi, right? Phi double dot in the k direction. In addition, finally, the acceleration of the center of the disk, which is the acceleration of B, is y double dot in the j direction. We could also calculate the acceleration of the center of mass of the bar, right? But turns out we're going to take moments about this pin joint, and that equation will decouple, as we'll see later. Now let's go and look at the free body diagram. So we have these forces that we've identified previously. I want to go and actually, write down what they are. Okay, so for the spring and the damping force, well, the spring force here, if z is positive, that means A moves down, this force moves up, and it can be written as K times Z, and to that I'll add the damping force, B times Z dot in the J direction. Now, the reaction force, again, we're going to take some of the moments about this point, right? So I'm just going to leave that as R. I could write that in different components, just like I will for the reaction force at B. Right? So here, this reaction force, I'll break that up into components in the I and components in the J direction, which means that on the disk, that force is minus px in the I direction, minus py in the J direction. Finally, I have the moment mk and minus mk acting on the disk. All right, so again, just to note that we have expressed P, this reaction force at B, in terms of I and J. I could also express this force in terms of E1 and E2. I would have an unknown component in the E1 direction and an unknown component in the E2 direction, and everything would still work out, right? I would just be solving for different components of the same force. Just to review, this connection between the disk and the bar, if it's rigid, then the moment is unknown, right? It's one of the things that we have to solve for. But in that case, we do have a constraint equation between the rotation of the disk and the rotation of the bar. Namely, those angles have to be the same. So, in fact, the angular acceleration of the bar and the disk are identical. In contrast, if the disk and the bar are pinned, well, pinned connections support no moment, right? So m is, by definition, equal to 0. But in that case, I no longer have a relationship between the rotation of the bar and the rotation of the disk. Those two things can be different. So here, in boxed in yellow, are the two constraint equations that I'll use in these two cases, right? So depending on the problem that I want to solve, and I'll go back and remind you, the first problem is where they're rigidly connected, and the second problem is when they're just pinned. So again, depending on which problem I'm solving, I'll use one of these two relationships. Okay, well, let's go and finally write down the equations of motion. So what are we going to do? Well, angular momentum balance on the bar and we'll take that about 0.0, right? This pin joint, this pin connection between the bar and the ground. And again, the reason we do that is so that the reaction force drops out. Right, so that'll be one relationship that we choose. And then we'll have angular momentum balance of the disk about its center. So that's at B, right? Because after all, in both cases, the disk rotates. It might rotate along with the bar if they're rigidly connected, right? Or it might be free to rotate if they're pinned, right? But still rotates. And then finally, because the center of the disk moves, we need linear momentum balance on it. So again, by taking angular momentum balance on the bar about O, we have eliminated the reaction force, R at O. Now, if we needed that, if I wanted to find out what this reaction force is, I could always go back and use linear momentum balance on the bar, and that would give me the reaction forces in terms of the motion. But now notice that we're going to take angular momentum balance of the bar about O, so we'll need the moment of inertia of the bar. Right, so that's going to be the moment of inertia of the bar about 0.0. And here, we know it about the center of mass, right? We've developed it about the end, right? But for any other point, we've got to go and calculate that. So we'll just use the parallel axis theorem. So it's the moment of inertia of the bar about the mass center plus the mass of the bar times the distance between G and O, right? So basically, if you think about this vector, R of O with respect to G, then we just want the magnitude of that squared. Okay, well, we can do this. So the moment of inertia of the bar about 0.0 is ml squared over 12. Right, we already said that's the moment of inertia about the center of the bar, plus m of the bar, that's m1, times the distance squared. Right, so that's L over 4 squared, which when you do the algebra here, you end up with 7 m1 L squared over 48. So notice what we're doing here, though. We're focusing angular momentum balance on the bar, right? So we're just looking at the bar. What happens to the disk? That's going to be taken care of by these second two equations, right? So I don't need to worry about the moment of inertia of the disk because I'm just calculating the angular momentum balance of the bar itself, right? Again, the effect and the coupling between the disk and the bar will come into play in these reaction forces and moments. So when I calculate this moment of inertia, it's just of the bar. Okay, well, you know what? We're ready for the equations of motion. And let's actually start off with the disk. So linear momentum balance, sum of the forces on the disk is the mass of the disk, right, times the acceleration of the mass center, right? So that's point B. Okay, now we'll just incorporate everything we have here. There's only one force, really two components, right? So we have minus px in the I direction minus py in the j direction. And that's going to be equal to m2 times the acceleration, y double dot, in the j direction. And notice here that I have components in the I direction and components in the j direction. The j direction we're actually going to save for later, right? But just looking at the I component, I only have px on the left-hand side, and on the right-hand side I have 0. Right, so immediately we see that px is equal to 0. There's no reaction force in the I component, again, for these linearized equations of motion. Now let's look at angular momentum balance. Right, so we'll take the sum of the moments about B is the moment of inertia of the disk about point B times the angular acceleration of the disk. Well, the only moment that acts about B is due to the reaction moment. So that's minus m in the k direction. For the disk, its moment of inertia is mr squared over 2 times the angular acceleration, which is phi double dot, in the k direction. Once again, we're trying to do these two problems at the same time. Later on, depending on what I choose for the connection, I'll either be fixing m or I'll fix phi, right? But for now, we're, again, doing them together. Okay, so now let's go and look at the bar. Well, we're going to take some of the moments about point O, which is going to be the moment of inertia of the bar about point O, times the angular acceleration of the bar. Okay, so now we need to calculate a number of different moments. Let's look at the spring and damping force first. Remember that moments are defined as R cross F. Right, so we'll have the moment of the spring and damper acting about O. Well, that's going to be the position of A with respect to O, right? So that's minus L over 4 in the E1 direction, cross the force, Kz plus B times Z dot in the J direction. Then we'll have the moment due to the reaction force at the end of the bar. Here I'm going to go ahead and set Pz equal to 0. The moment arm is 3L over 4 in the E1 direction. And the force, of course, is Px plus Py in the J direction, but we've already said that's equal to 0. And then finally, I have the reaction moment. Right, so that's going to be m in the k direction is equal to, well, the moment of inertia of the bar about point O times theta double dot in the k direction. So here we need to evaluate these cross products. E1 is cosine of theta in the I direction plus sine of theta in the j direction. And E2 is minus sine in the I direction plus cosine in the j direction. So when we go and evaluate these cross products, and we're going to linearize at the same time. So notice that E1 is a component in the I direction plus a component in the j direction. Well, the j term drops out because I have j cross j. Now, this is assumed to be small because, again, we're linearizing for small displacements. So we're just going to take the dominant term in the I component. And so I cross j is equal to k, and this reduces to minus L over 4, k times z plus b times z dot. Again, I've made the assumption here that the angle is small, so cosine is approximately 1. Now, the next term, again, E1 cross j is going to be I cross j, right? So we'll have 3L over 4 times py, and then plus m, all of that in the k direction, is the moment of inertia, which we found previously was 7m1L squared over 48 times theta double dot in the k direction. Okay, so up to now, right, we've been able to do both problems together. And we find equations of motion here, right? We find this term, and then finally we have this from angular momentum balance on the bar. So we have these three together with our constraint equations previously. So I've rewritten those here, right? Again, this is linear momentum balance on the disk, angular momentum balance on the disk, angular momentum balance on the bar, and my two constraint equations. So here, I'm actually going to eliminate everything except m and phi, right? Because that has to do with the different constraints that we have. So I'm going to eliminate py, right? I'll take this and I'll substitute in. And then I'll choose to eliminate z and y, right? So I can write a single equation in terms of theta, and then we'll also have m and phi, right? So let's do a little bit of algebra, right? I'd say pause the video, maybe do this yourself, right? But again, we'll make use of that. We'll make use of these constraint equations. And what we find is 7m1 L squared over 48 times theta double dot, right? That comes from right there. Now, the next two terms will be due to the spring and damper, right? And that ends up being written as L squared over 16 times k theta plus b theta dot. And then I have a term that comes from this reaction, and when I simplify, that reduces to 9 m2L squared over 16 times theta double dot. We still have this m, right? And I brought everything to one side, right? Equals 0. And then finally, we have this equation for m. M is equal to minus m2 r squared over 2 times phi double dot. Okay, so now finally I'm at a point that I want to distinguish between these two problems, right? But again, here this whole lecture is devoted to looking at the effect of internal constraints. So if we have a rigid connection, well, in that case, we've said that phi double dot is equal to theta double dot, right? Or really we said phi is equal to theta, but taking two derivatives, we get this. Okay, great, right? I can just take this, use it in this equation for m, right? So this becomes minus m2r squared over 2 times theta double dot into this equation, and we get the following. Notice we have a lot of theta double dots here, right? I've got 7m1 L squared over 48. I've got another one, 9m2 L squared over 16. And then finally, I have plus m2 r squared over 2. Theta double dot plus b L squared over 16 times theta double dot, right? That's due to the damping. Finally, KL squared over 16 times theta is equal to 0. So this becomes the equation of motion if I have a rigid connection. And one thing that I'll point out is that if you were to go and calculate the moment of inertia of the entire object about point O, right, this pin joint, this is what you'd find, right? This is exactly the moment of inertia of the body about point O, right? So if I treated this object as just one composite object, then this would be the moment of inertia that I would use. So it really reduces back to the approach that we took in our composite objects lecture. Now, if we have a pinned connection, well, in this case, the moment vanishes, right? So m is equal to 0. So here we find that phi double dot equals 0. So this disk can rotate, right? But if it does so with constant angular velocity, right? So there should be a constant rotational speed that was determined by the initial conditions. Of course, we're neglecting all of the dissipation that might exist at a real pin joint and things like that. But under these assumptions, this is the behavior of the disk rotation. Now, going back to this equation, well, m is equal to 0, right? So what's left is 7m1 L squared over 48 plus 9m2 L squared over 16. And then theta double dot, we again have the damping, and we have the stiffness. KL squared over 16 times theta equals 0. So we now have a different equation for the behavior of the bar, right, when we have a pinned connection. And the difference is precisely this additional factor of m2 r squared over 2, which represents the moment of inertia of the disk about its center. Now, notice that if r goes to 0, right, in the rigid connection, then we recover this equation for the pinned connection, right? So essentially, this pinned connection implies that the disk is equivalent to a point mass. In terms of its effect and influence on the motion of the bar, right? So essentially I could replace this physical thing, this disk, with an idealized point mass, and I'd get the same equations of motion, right? So from a dynamic standpoint, those two systems are entirely equivalent. So that's it, right? This is a pretty involved lecture. I've actually done 2 problems all at once, right? It's kind of buy one, get one free. And in doing so, I'm able to highlight the influence of the different kinds of connections that we might have between objects. So if it's a rigid connection, that implies that the two objects rotate together. While if it's a pinned connection, right, that implies that the moment at the end of the bar or at the connection point is equal to 0. Okay, so that's it. As always, feedback is appreciated. Thanks for watching along. And if you have any questions at all, right, please let me know. Thanks so much. Take care. Bye.